Hello everyone, welcome to the course of Vlsi design. In this, we are going to see introduction to the Vlsi design in this lecture. The contents of this lecture are, it starts with what is Vlsi and why Vlsi is required, then advantages of Vlsi, applications of Vlsi, then the basic law which is used in Vlsi is Moore's law. So what is a Moore's law? And we are going to see Vlsi design flow, then different opportunities in the Vlsi domain and Vlsi industry. Let's start with what is Vlsi. Vlsi abbreviation is very large scale integration. Vlsi abbreviation is very large scale integration, and it is the process of integrating or embedding. It is the process of integrating or embedding hundreds of thousands of transistors on a single silicon semiconductor microchip. So Vlsi is a process of integrating hundreds of thousands of transistors on a single silicon semiconductor microchip. It is a process, and it was conceived in the late 1970s when advanced level computer processor microchips were under development. This Vlsi was started in the late 1970s. So first Vlsi IC started in 1979. Then example for the Vlsi chip is microprocessor. Microprocessor and microcontrollers are example ICs for the Vlsi chips. Before the introduction of Vlsi technology, most ICs had a limited set of functions they could perform, because Vlsi is having a more number of transistors on the chip. With a more number of transistors, more functionality can be designed. Before the Vlsi, SSI, MSI, LSI we had, and in those three number of transistors are less, therefore the minimum or limited functionality can be achieved with that MSI, LSI and SSI ICs. So therefore Vlsi is overcoming the disadvantage or limitation of LSI, MSI and SSI. Then an electronic circuit, example, an electronic circuit might consist of CPU, ROM, RAM, that means memories, and other glue logic, that is any interfacing circuits. If electronic circuit is having all these means, it's definitely it can be implemented and designed with the Vlsi IC only. So Vlsi lets IC designers to add all these onto a single chip. That is example our computer. In that computer we are going to have CPU, memories and other circuits. All those can be embedded on a single floor using the Vlsi chip. Then Vlsi is successor of the circuits like Vlsi is the successor of the integration technologies like LSI, MSI and SSI. Whereas LSI is large scale integration, MSI is medium scale integration and SSI is small scale integration. Let's have a look of what is SSI, what is MSI and what is LSI, and then Vlsi and etc. Started in the 1984. And the number of transistors or the number of logic gates can be defined for each and every logic level. For the SSI, the number of transistors are having of minimum 1 to maximum 10. And if you are seeing the logic gates number, minimum 1 gate to 12 logic gates can be embedded on the SSI chip. Similarly, MSI means it is having of 10 to 500 number of transistors, minimum of 10 and maximum of 500, or 13 to 99 number of gates on that microchip. So whereas LSI is having of these many transistors, that is 500 to 20,000, and gates count is 100 to 10,000. And VLSI is having a transistors count of 20,000 to 1 lakh of minimum components of transistors on the single floor, and gates means 10,000 to 10 power 6 gates. So here it is, if we observe here, the range from the minimum number to maximum number is bigger, variation is bigger. That means a circuit which can be implemented with LSI can be implemented with VLSI, and bigger circuits also can be implemented with VLSI because it is having of more number of transistors. With the VLSI, starting from the lower end application to higher end application can be implemented because it is having a range of 20,000 transistors to 10 lakhs of transistors. It means it is having of more range, that is from the low end to the high end. Whatever the circuit can be implemented with LSI, the same can be implemented with VLSI, and much more circuitry also can be implemented. And then ULSI is having of much more number of transistors than the VLSI, but low end applications cannot be implemented with the ULSI. So therefore, this VLSI has become an important technology because of this feature. A wide range of transistors on a single floor or wide range of gates on a single floor can be possible. Therefore, starting from the medium end or low end application to higher end application can be implemented. So that's why this is a very important, and it became the important one. So we are going to study this VLSI. Why this VLSI? Because of this VLSI, integration improves the design. Improves the design means speed will be improved, area will be reduced, and power will be reduced. So this integration itself is having an advantage of all these parameters. In this VLSI again having all these parameters. So it improves the design part. Because of the low parasitics, it is giving higher speed. And because of the integration, it is having of low power consumption. And because having all the same type of the components on the same single floor, it is physically smaller. Having a more number of transistors on a small chip, implementation can be possible with this VLSI. So it is physically smaller when compared to the discrete components. And this integration reduces manufacturing cost. That is, there is no involvement of manual assembly, fully automatic. That's why manufacturing cost is reduced. The two, these VLSI chips are produced in mass production. Therefore, the cost of the ICs are still reduced. So see this picture. This is actually VLSI advancement. Because of the VLSI advancement, this much advantage we got. This left side picture, this is the first hard drive shipped by the IBM with the capacity of a 5 MB, 5 megabytes of the memory is this much of the size. This was happened in 1956. Whereas see the right side picture, this is more than 5 TB terabytes, 5 terabytes of the memory, but within a less space. This is a portable device. This is the portable one also, portable hard disk. So within the portable size, portable nature and with the small size, and compare the memory capacities. It is 5 MB but it is 5 TB terabytes of the memory. So this was happened because of the VLSI advancement only. And see the another example. See this. This is the first electronic computer which was implemented in 1946. This is the computer, and This is the computer, and now see the laptops or desktops which are in the sizes. So size is drastically reduced because of the VLSI. When size is reduced, automatically power will be reduced and speed will be improved. So speed is also improved in our laptops and palm tops and etc. when compared to the first computers which occupied the more space. Because of the VLSI, this was happened. And another example, this is the first Apple computer in 1976, and now in 2011 this was the Apple. Compare the sizes. This was happened because of the VLSI only. All these are because of the advancement of the VLSI. The semiconductor industry and electronic devices became this much of smaller. Coming to the advantages of VLSI, which we have seen now, the size reduction, so that power and delay all became the advantages. So therefore advantages are, it reduces the size of the circuits, so it occupies a relatively small area, and it reduces the effective cost of the devices, and it takes less power and it dissipates also less power. So it requires less power than the discrete components, and it is giving the higher reliability and delay is reduced. All these are advantages of VLSI. Coming to the applications part, applications of VLSI. What is VLSI? Already we have seen VLSI as a process of embedding or integrating many components on a single chip. The same. So because of that, it is called as an implementation technology. It is of an implementation technology for electronic circuitry of either analog or digital, and it is concerned with forming a pattern of interconnected switches and gates on the surface of the crystal of a semiconductor. Because of this nature, this can be used in so many applications like microprocessor IC is application of VLSI IC. So microprocessors, personal computers, microcontrollers, and memory devices like DRAM, SRAM and all the memories. Then special purpose processors called as ASICs, application specific integrated circuits. ASIC abbreviation is application specific integrated circuits, like examples of CD players, DSP applications and some medical and healthcare applications also. Then it will be used in the optical switches. So it has made highly sophisticated control systems mass producible and therefore cheap, because microprocessors is a mass production IC of 8086 or 80186 or Pentium processors etc. So that because of that mass production, the cost of these ICs are reduced. So VLSI permits this mass production so that cost is reduced. So VLSI ICs are cheap also. Because of using of these many application circuits, those will be used in the fields of voice and data communication networks and digital signal processing applications, and in the field of computers, in the field of commercial electronics and automobiles, and finally in the medical and healthcare sector also. In voice and data communications means everyday we are using, example sake, everyday we are using mobile. In mobile there is a chip, there is a processor chip. That processor chip is VLSI. And a mobile is using for the voice, that is for the audio call, and the same is using for the texting and sending of data and sending of images and videos, that is nothing but data communication. So once a VLSI chip is using in a mobile means that VLSI is using in the mobile and voice and data communication systems. Then that will be used in the digital signal processing. That means in all our communication networks, our signal is going in the digital transmission. there definitely that signal is going to be processing. So therefore in the all communication parts, this digital signal processing is involved, like audio processing, speech processing, video processing, in all these applications. Then computers are nowhere without VLSI, because in the motherboard we are having a processor IC. That processor IC is nothing but VLSI IC. Processor IC is VLSI IC. Then in commercial electronics means, example, all our home appliances are commercial electronics. That is starting from the refrigerator to, in our homes, refrigerator or washing machine and dishwasher, etc. In all these, processor chip is used, controller is used, that is nothing but the VLSI IC. And in automobiles, that means in all our cars we are having of automation process, that is with the VLSI IC, controlling, regulation, all these are implemented with a circuit. That circuit consists of VLSI IC. And in the healthcare sector, like whatever the devices, example sake, a pacemaker device which is used in the heart problems. So this device is also a VLSI IC. Like body sensor nodes or the devices of VLSI only. So like this, VLSI is used everywhere in the all fields of the engineering. These are the example chips, VLSI chips, the pictures of VLSI chips. This is a one IC, another IC and another IC. Like this, we will have the VLSI chips on the boards of the PCB in our computers and in our all the devices which we have seen, or all the applications which we have seen just now. Then the size of the VLSI chip. What is the size of the VLSI chip? With 20 nanometer transistor length, we can fit around 250 billions of the transistors on single silicon floor, that is around the size of our fingernail, this much. So with the 20 nanometer, example sake we are telling here 20 nanometer transistor size, but transistor size may be anything, that may be 180 nanometer, 90 nanometer or 45 nanometer. With this, around the 250 billions of silicon wafers is the size of the around 1 hour finger nail size. That size was reduced, that means that many silicon wafer, 250 billions of silicon wafers are possible with our fingernail size because of the reduction of the transistor size and including the number of transistors on the same floor. So that was actually predicted by one person, that is Gordon Moore. He predicted one rule for the number of transistors components increasing on the semiconductor chip for every 18 months is predicted, that is Moore's law is Moore's perception that the number of transistors on a micro chip doubles for every 2 years. And then this was because of the advancement of VLSI, this was actually crossed this rule, this perception and this prediction, and it reached to a level of exponential. That means number of transistors on a floor are increased exponentially. Because of that reason only, those many circuits became the smaller size. So here with this graph we can understand that over the years the number of transistors on a single chip are increased exponentially. So starting in 1970s and late 1970s, that is in 1980s, it is having of the number of components of some around 20,000 on a chip, and that is at the time of inception of the microprocessors of 4004 and 8008 and etc. Then drastically the transistors are increased. Now it is in the range of 10 power 9 transistors per the chip at the time. So this is because of increasing more number of transistors on a unit area, the sizes of all the devices reduced drastically. And why or how this number of transistors are increased, embedded on a single floor or a unit area? Because of the reason of reducing the transistor size. So this is again the year and the size of the transistor, that is gate length. It is generally represented as L. Based on this gate length defines the transistor size here. So since the transistor gate length is reduced, therefore many number of transistors are embedded on the same floor. So therefore the more number of transistors with unit area, the size of all the devices are reduced. Now it is in the size of around 5 nanometer to 4 nanometer and etc. The size of the present today's gate length is at around 4 nanometer, 3 nanometer size. The factors considering in VLSI design are, the main factors are only 3. Those are power, speed and size. Because of having all these features, it automatically getting the less cost because of the mass production of those ICs. So power is reduced in the VLSI and speed is increased in the VLSI and size is reduced and cost is also reduced. Or while designing a circuit, before starting the design of this circuit, a designer has to concentrate on all these parameters in such a way that power has to be reduced, speed has to be increased, area and cost has to be reduced. So all these factors are already achieved in the VLSI, therefore it improves the size, speed and power. Means the size is reduced, speed is improved and power is reduced. So automatically because of mass production, cost is also reduced. So this integration reduces manufacturing cost because of no manual assembly and mass production. Coming to the VLSI domain, it is having of 3 domains. One is the design domain, second one is the CAD tools domain, and next one is the technology domain. So one can find an area to work of all these 3 domains. Here design domain will do circuit design and programming and analysis, and CAD tools domain will work with tools used to design for circuits and layouts. This is dealing with the tools part, CAD tools. And technology domain is working with manufacturing part. That means if you want to go for industry to work under VLSI, one can choose any one of these 3 domains. In the design part, what is actually the exact difference of design, CAD tools and technology domains means, if you want to have one application, one IC, for example, a microprocessor IC. If you want to have a microprocessor IC, then at the design part in the design industry is going to design it for the given specifications. Specifications will be taken and its architecture will be redesigned, and the all circuits of that microprocessor chip will be designed there. And then, so once design is completed, then where is the verification part? For the verification of the designed circuit will be done by CAD tools. Right? In our campus, we have CAD tools for the VLSI as cadence tools. In the cadence, Virtuoso tool we have, and NC-Lance tool we have, and Ashura tool we have, and like this we have so many tools. And in Xilinx also we have ISC and Vivado for the VLSI tools. So what is the use of these tools, or what is the purpose of these tools means for the verification of the design which is designed by the design part. Verification means this verification is going to be performed using the simulation process. So after simulation we are checking the functionality check, then after having of so many timing simulations, functional verifications and etc., the complete design is going to be tested using the simulators, and those are called as the tools. Here for these tools also there is a scope for the improvement always. So at this the designers are going to design the tools part also, developing the tools, advanced tools, so that becoming the testing is easier for the designer, and embedding so many parameters, having of so many analyses in a tools means that circuit will be tested for all the parameters by the designers. So there is a scope for development of this CAD tools is one area. Then finally what we need hardware chip for this microprocessor. So hardware chip, for that fabrication industry required. So fab industry is doing this technology part, that is going to be fabricated for the given file. That given file is in the form of GDS2 file that was generated from the layouts actually. Those layouts will be generated by these CAD tools with the help of the designers. Then for that IC is going to be fabricated. That fabricated IC will be used as an application in our circuits. Then at the manufacturing industry also there is a scope of the development and improvement, that is in the technology wise, reducing the technology from 180 nanometer to 90 or to 3 nanometer and etc. So there is a scope for these three domains. One wants to go into the VLSI domain and VLSI industry. For all these industries, for all these domains, we have this is the three domains of VLSI. Using all these three domains, one VLSI chip can be designed. So VLSI design flow can be seen with the help of this figure. That is, in this, starting from an idea, its specifications can be taken out and architectures can be designed, or circuits can be designed to meet these specifications, and then those architectures are verified and designed and captured using the RTL coding and then simulation and then synthesis part. So by using this RTL coding and verification synthesis, we are getting of hardware circuit here, hardware of netlist. Then that hardware can be fabricated by using the foundry, and after having of hardware from the foundry, it is going to be called as a chip after its testing. After foundry also it will be tested. If it passes in the test, then only that will be goes into the market as the chip. So this is a design flow for a layman perspective who are the out of the scope of VLSI. Now if you want to see actual VLSI design flow for a Asic, this is the Asic design flow. Here first starts with system specifications. System specifications means as a block What are the inputs, what are the outputs, what are the power constraints, or timing constraints, or static constraints, and etc. So many constraints will be taken in the system specification part, and then to meet those system specifications, architectures will be designed. Architecture will be designed, and for that architecture, designed architecture will be captured by the using of a code part or a logic part or a circuit part. That is nothing but functional design and logic design. Then that logic design, actually to fabricate an IC, layout is required. For that layout, transistor level circuit is required. So therefore that logic design will be converted into a circuit design. Then after circuit design, it goes into the physical design, whereas backend process starts. In this physical design, there are so many steps like partition, floor planning, placement, routing, and etc. By using all those sub steps, this physical design will be completed. Then after doing that, verification at the physical level also is doing, if it's satisfying the system specifications. Then going to the layout post processing. After post processing, if it is giving the correct result, then it is going for the fabrication part. After fabrication, it goes into the packaging and testing part. So if it passes the test, it will come to the market. Here left side, if you see these figures, this is the block diagram level. Block diagram level is nothing but the specifications part. Then it is going to the architectural design part. By capturing, it will be captured with the help of a HDL. Example say here HDL is showing. So hardware description language of VHDL are very long. Anyone can be used to capture that architecture. Then that will be converted into logic design. Then that logic design will be converted into circuit design. Then that circuit design will go to the physical design. In that physical design, placement, floor planning, routing, all these will be taken care. Then this is actually like layout, and that layout will be verified with the help of tools like DRC checkers, LVS checkers, and ERC checkers. Then if it passes, in that case, it will go for the fabrication part. After fabrication, it will go to the packaging. This is a package, and then testing part. If it gives the correct result, then it will come to the market. This is the Asic design flow. Whereas in this physical design is having of so many steps. Whereas in this physical design is having of so many steps. So those physical physical design steps are these. One is partitioning, floor planning, placement, clock tree synthesis, signal routing, and timing closure. So with the help of all these, this physical design is performing. Actually, this physical design is one complete area of requirement in the industry where we can do all these things. Okay, so now for all these steps, these are divided into two ends. One is front end and another one is back end. So design flow is of having two parts. One is front end, another one is physical end. Starting from the physical, it is called as back end. Back end. You can have the opportunities to work in the front end part and in the back end part. That means, see, it is having of front end design and back end design. Front end design is designing and testing the circuits with use of CAD tools, and back end is using the physical design part, that is developing and fabrication part. And it is too costly. The back end is too costly when compared to the front end. So if you get an opportunity to work in the back end, you can get more packages also. So after back end, our design will be available as product, and after front end, your design will be verified and circuit is ready for that. So then layout will be designed at the back end, and that can be goes to the fabrication industry for the getting of this product. For doing of these front ends and back ends and all these VLSI designs, the fabrication parts also, we have so many companies in our India. So the companies, VLSI companies which are available in India, in that examples, so Cadence, Xilinx, AMD, Microchip, Synopsys and etc. Intel, all these are having the VLSI product and VLSI part in their companies. So you can get an opportunity to work in all these companies if you do the VLSI. Till now we have seen the introduction to VLSI part and advantages and applications of VLSI part and the VLSI industries and VLSI domain. I hope you understood this. We will continue in the next class. Thank you. Hello everyone, welcome to the lecture of Basics of Mass Transistor in the course of VLSI design. The objective and outcomes of this Basics of Mass Transistor lecture are: students will try to learn the basics of mass transistor like the N channel and P channel MOSFETs, that is NMOS and PMOS transistors, and mass transistor symbol, mass transistor circuit and its applications like switch and amplifiers they are going to learn. And after learning of this lecture, students will be able to understand the types of mass transistors and mass transistor symbols and advantages and disadvantages of mass technology and applications of mass transistors, etc. The contents of this lecture are: it starts with introduction to mass transistor, then the mass technology, and it covers the types of mass transistors like NMOS transistor and PMOS transistor, and the structures of both NMOS and PMOS transistors, and we are going to see the symbols of both NMOS and PMOS transistors and applications of mass transistors, advantages and disadvantages of mass transistors we are going to see in this lecture. and T, FET. So MOSFET abbreviation is Metal Oxide Semiconductor Field Effect Transistor, and it is a semiconductor device. It is a transistor and it is a device of semiconductor device, and it is using mostly in the digital design. So it is a most important device in digital design. It is acting as a very good switch. Because of this good switching behavior, it is used in digital design circuits, and it is relatively having over few parasitics, so therefore delay is less and power consumption is also less, and it is having of high integration density, that is number of transistors per unit area is also more. Therefore, it is having of high integration density, and its manufacturing is simple and economical also because of mass production, and it is cheaper for the large complex circuits. And this MOSFET is used in a technology is called as a mass technology. In our semiconductor industry, the names are called as technologies, where if mass transistors are used, it is called as mass technology. Like if NMOS transistors only used NMOS technology, and both NMOS and PMOS transistors used, that is called CMOS technology. Or if BJTs are used, that is called as bipolar technology, and BJTs and CMOS, if both are used, that is called as bi-CMOS technology. Like that, in the mass technology, only mass transistor is used, and that mass is a given name because of its structure, that is metal oxide and semiconductor. The structure of metal electrode over an oxide insulator over a semiconductor surface. That is, metal layer is one layer and it is constructed over the semiconducting insulating layer of oxide, and it is constructed over the semiconducting layer of silicon. So because of this structure, because of its structure, it is a given name of mass. And in this mass technology, the user transistors all are MOSFETs only. Its structure is represented by using this figure. See here, this is the one layer of metal layer, the first layer, then oxide layer, and then semiconducting layer. It is a semiconducting layer and it is the metal oxide and semiconducting structure. And generally this metal layer is used as either aluminum or polysilicon here, and olden days aluminum is used as a gate, now polysilicon is using, and this oxide is silicon dioxide is used, and the semiconductor is either N-type or P-type of silicon substrate is used. And here the source and the drain will be taken from the substrate structure, and the gate is ended with on two ends, source and drain parts. Now this is a working on a one principle, that is equal to the mass capacitor action, because the metal layer and semiconducting layer means both metal layers. In middle some dielectric is there, that is insulator. So two conducting plates and dielectric acting as a capacitor action. That action is the electric field on the metal electrode side of the oxide insulator. That means electric field on the metal electrode side of the oxide layer is having the effect of the substrate resistance. So if I apply a voltage here, it affects the resistance of the substrate. So resistance of the substrate is going to be affected. Resistance will be increased or decreased based on the potential applied at the gate terminal. This is nothing but the capacitor action. Using this action, the mass transistor is working. The in detail working of this mass transistor we will see in the later slides. The advantages of Pmas technology are most of the Pmas digital ICs are constructed entirely of the MOSFETs. That means the MOSFET will be acting as a transistor or a resistor or a capacitor, etc. The same MOSFET can be used as all these active or passive devices. And this MOSFET can also be used as a diode also. That means in the place of each and every component which is used in a circuit, that can be realized and implemented with the Pmas transistor. Because of this reason, total IC is built with MOSFETs. This is the advantage. Because of the same MOSFET constructed on the floor, it is going to save area and it is going to have the symmetry in the layouts. So design process is simple and fabrication process is simple. So because of that, cost is less, and because of that, mass production is also possible. So because of having the only MOSFETs on the entire chip, it is simple circuit and inexpensive to fabricate. And it is having of high density of the fabrication, means more number of transistors can be accommodated, and it is having the low power dissipation. These are the advantages of Pmas technology. So we are going to see these advantages are coming because of the using of MOSFET transistor. So we are seeing in detail about this MOSFET transistor. Before going to see the MOSFET transistor, let's see the definition of the transistor and types of the transistors. A transistor is a semiconductor device used to amplify or switch the electronic signals and electrical power. In the analog applications, it is using as amplifier, and in digital applications, it is using as a switch. And the transistor is always a semiconductor device. And it is composed of at least 3 terminals. It is a semiconductor device and which is having of at least 3 terminals. And these terminals are used to connect to the another external circuit. Now, let us see the basic type of the transistors. Basically, there are 2 different types of the transistors. One is bipolar junction transistors and another one is field effect transistors. Field effect transistors, that is BJT is one type and FET is another type. And in the BJT, there are 2 different types of the transistors. One is NPN and another one is PNP. And in the FET, there are again 2 types. Those are junction field effect transistor JFET and MOSFET, metal oxide semiconductor FET. Our transistor is this one. So in the FETs, one kind is MOSFET. Let us see the type of these MOSFETs, type of the MOSFET transistors. So MOSFETs are having of 2 types. One is enhancement type, another one is depletion type. And again in the enhancement type, 2 types of the transistors are there. One is N-channel transistor, another one is P-channel transistor. And in the depletion also there are 2 types. One is N-channel and another one is P-channel. That means in the MOSFET we have 4 different types of the transistors. They are N-channel enhancement MOSFET, P-channel enhancement mode MOSFET, N-channel depletion mode MOSFET and P-channel depletion mode MOSFET. 4 different types of transistors are there. These are the practical transistors, figures, just figures. The packages are different here. These packages are different, but all are having of 3 terminals or 4 terminals. These MOSFETs are having of minimum 3 terminals and it is having of maximum 4 terminals. The fourth terminal is bulk. The other 3 terminals are gate, source and drain. So some of are with 4 terminals is represented and some are with 3 terminals represented. We have seen the types. What are those types? One is a depletion and another one is enhancement. What is the meaning of depletion and what is the meaning of enhancement type? Depletion is nothing but if the channel is created physically, then that is called as depletion mode MOSFET. And enhancement means if the channel is created electrically, then that is called as enhancement mode MOSFET. In the sense, at the time of the fabrication itself, the depletion mode transistor is having a channel, and enhancement mode MOSFET means after fabrication, by applying the voltages, that is electrically, by applying the voltages at the gate terminal, the channel is going to be created. That is called enhancement mode MOSFET. So channel inbuilt is called depletion. Without channel, after fabrication, having the channel with applying the potential is called the enhancement mode. And so in this again, we are telling the channel, this channel may be of the type NRP. So if the channel is N type, then that transistor is called as NMOS transistor. If the channel is a P type, then that is called as Pmas transistor. So NMOS with enhancement and depletion, Pmas with enhancement and depletion. Finally, we are having of 4 transistors. And these MOSFETs of NMOS or Pmas or enhancement or depletion are used in ICs. And in those ICs, enhancement MOSFETs only used because depletion MOSFETs are initially acting as the on switches. So because of on switches, they may be use some power and etc. So to avoid all those, only enhancement MOS transistors are going to be used in MOS ICs exclusively. And these enhancement or depletion MOSFETs modeled as a 3-terminal transistors. Those 3 terminals are, one is the gate, another one is the drain and the next one is the source. And if we are using the 4th terminal, that is the bulk terminal. The 4th terminal is bulk and it is acting like voltage controlled resistance. So MOSFET is acting as voltage controlled resistance. Let us see the symbols of the MOSFETs, enhancement and depletion and P type and N type. The symbols show with a broken line like this are the representation of the enhancement, and whereas the symbols of these thick lines represent the depletion. So MOSFET enhancement transistors with the 4 terminals are the first set. Then MOSFET enhancement with bubble and without bubble is the second set. This is with the current direction representation of arrow marks the 3rd set, and 4th set is the depletion transistors with the 4 terminals is showing. So in the first set, the Pmas and Nmas represents the different arrow directions. This is the Pmas transistor and this is the Nmas transistor. Nmas enhancement, Pmas enhancement. Enhancement is representing with broken line of the channel. It is representing the 4-terminal transistor. Then 3-terminal transistors of Pmas and Nmas. Nmas is representing without bubble and Pmas is representing with bubble because this bubble is representation of the complement, whereas N and P both are the complement to each other. Then the next set is representing only 3 terminals with current direction on the source terminal. So this is the NMOS. In this, current is flowing from channel to the source outside, and this is the PMOS where the current is entering into the channel from the source. All these three sets are representing the enhancement mode transistors. Then it is representation of the depletion mode, where this depletion mode represents the thick line for the representation of the physical channel. So this fourth set will be used for the depletion mode transistor representation for the first set of enhancement mode transistors. Whereas in these two sets, if we want to represent depletion mode transistors, then extra line is going to be used at the channel part. That is, I am representing like this. These four are originally enhancement. Now if you want to represent as a depletion, one thick line is used extra here. So this is the representation of the depletion transistor for the both NMOS and PMOS with 3 terminals with the bubble and without bubble representation. Similarly, so this line is representing the depletion mode transistors. And in the third set also, same arrow mark, but the channel is represented one thick line for the depletion mode. Physical existence of channel is represented with this thick line. This is also depletion mode transistor symbols with the arrow of 3 terminal transistors. These symbols are used in our different books. So we are going to use any one of the set for the representation of the circuits. Now let's see the structure of MOSFET. Before going to see actual 3-dimensional structure of the MOSFET, just to see schematic structure, the front view of our MOSFET transistor. The schematic structure will look like this. That is, having a metal layer, oxide layer and semiconducting layer, 3 layers. And this metal layer and oxide layer defines the gate area. So this is the gate. To this gate, on both ends, source and drain terminals will be used. This is the source and drain. So this part is representation of the source and this part is representation of the drain. In between source to drain is representing the area called channel. This channel is nothing but a conducting path or a conduction path which is connecting both source and drain. A conducting path which is connecting both source and drain is called the channel. Channel length is representing as L and channel width is representing as W. That width we can see in the 3-dimensional model. So the front view or schematic view of the MOS transistor will be look like this. Now if you want to write this structure for NMOS, enhancement and depletion, or PMOS, enhancement and depletion, how they will be. Let's see those two structures also. One is the NMOS structure, schematic structure of NMOSFET for the both enhancement and depletion. This figure is representation of enhancement and this figure is representation of the depletion mode transistor. In the enhancement, we can find the difference between these two here. Clearly, there is no connection path and here there is a connection path physically. So this N plus and N plus is joined physically. This is the depletion. Whereas this N plus and N plus is not connected physically. This is the enhancement. So channel is created electrically here and channel is created physically here. Then what we are telling? Channel. Channel is of, in the NMOS, channel is of N. So N channel, here we need to get the N channel by the electrical connection, okay. So this N channel is connecting of source and drain means source and drain also has to be N. So N, then only we will have some connection, same one connection path. So N channel means both source and drain has to be N. Okay, so N channel means both source and drain has to be N. So in NMOS, source and drain are N plus. This N plus, this plus represents higher doping level. Higher doping level when compared to the channel part. Here also higher doping level is a representation of the when compared to the channel part. The symbol which we have seen already, the enhancement means broken line representation and depletion means decline representation, and 4 terminals, one terminal is gate, another terminal is source, drain, and the fourth terminal is bulk substrate. So 4 terminals are represented here, the both enhancement and depletion MOSFETs of the Pmas type. Let's see the Pmas type also. The difference between this and Pmas is nothing but the channel is going to be P. So the channel is P. Therefore, source and drain has to be P plus. If a channel want to become a P, then source and drain has to be P. So in Pmas, source and drain are P plus, channel is P, and channel is physically existing in the depletion mode transistor, and channel is electrically it has to be created, so there is no channel physically, that is enhancement mode transistor. This is the enhancement mode Pmas transistor symbol, and it is the depletion mode transistor symbol with broken line and without broken line. And here arrow mark defines whether it is a Pmas or Nmas. So arrow mark for the Pmas is outside to the bulk. This is the symbol, and in the Nmas the symbol is nothing but inside of the this. So now it is correct exactly. Nmas enhancement and depletion, and Pmas enhancement and depletion of the symbols. Now let's see the 3D structure of this MOSFET. 3D structure. This is the 3D structure representation, and in this source, drain, gate and oxide and semiconducting layer, and then channel area. This is the 3D structure. Same what we have seen in the schematic structure, same structure can be represented here also. Here we can see extra as a width of the channel or width of the gate. The length of the channel is distance between source and drain and the area under the gate. And so therefore it is called as channel length, or it is also called as gate length. Both are equal. And similarly, the width of the gate or width of the channel both are same. That is representation this side. This is the width of the gate. Width of the gate or width of the channel. So length of the channel and width of the channel. And the 4 terminals, one is the source terminal, one is the gate terminal, one is the drain terminal, and another one is the body or bulk terminal. Here for the gate, polysilicon or aluminum is used, and for the source and the drain, depending upon the transistor type, pentavalent dopant or trivalent dopants are used, and this is the semiconductor of silicon is taken, and then it is going to be doped to the required type, whether that if it is required as N or P, the respective doping will be used. Here the transistor size is defined with channel length and channel width W. Length is always fixed in the designs, and the W can be varied by the designer. And gate is made up of polysilicon or metal, and W is selectable by the designer. L is the minimum feature size. Bulk connection is used to ground in the Nmas and to VDD in the Pmas to avoid some problems, that is to prevent forward biased PN junction, that is to avoid the leakage. This is always either very high or it is very low. That means that is acting as high resistance or low resistance in 2 regions. One is on state and another one is off state. So on state is defined by the low resistance value and off state is defined by the high resistance value. So means To act or to work this Pmas transistor as a switch in the digital domain, using of these two properties, very high resistance and very low resistance, it will be used as on switch or off switch. That is, on switch or off switch of either the NMOS or PMOS transistors are represented here, and NMOS will be on when the gate potential is logic high and NMOS is off when gate potential is logic low for the NMOS transistor. Similarly, for the PMOS transistor, if gate potential is logic high, it will be off, and gate potential is logic low, it will be in the on condition. So on means low resistance, off means high resistance. High resistance is represented as open connection and low resistance is representing as short connection in both NMOS and PMOS transistors. Let's see this switch behavior in detail for the NMOS and PMOS transistors. The NMOS transistor acting as a basic switch based on its gate voltage, gate applied voltage. So this is the NMOS transistor, this is the gate terminal, this is the source terminal, and it is the drain terminal. Based on the VGS value, that means the gate to source potential, and based on the threshold value of this MOS transistor, NMOS transistor, VTN is called as threshold voltage, and Vin is applied at gate potential, that is between gate to source. So if VGS is greater than VTN, then only NMOS will be in the on condition. That is, VTN is a positive value. So when VGS is a positive, then only NMOS will be on. That means for the logic high, this will be in the on condition. And if VGS is less than the VTN value, then NMOS will be in the off. NMOS is off. Whereas VTN is a smaller positive, then lesser value means for the low values or zero values are negative values. That means for logic high, NMOS is on. For logic low, NMOS is off. Logic high means, that is generally it will be represented with positive potential. Logic low may be represented with 0 volts or negative volts. So for these two cases, this NMOS is in the off condition. Off is representing with open switch, on is representing with the closed switch. Let's see that. So this is the NMOS transistor and this is the VGS potential, that is the gate to source potential, and source is connected the low potential. Now this is on when VGS is for the logic high value. So for logic high value of VGS, this transistor is on. On is representing of the resistance of low. Here for example it is representing as 1 kilo ohms. And when input is equal to logic low, this is NMOS transistor is off. Off transistor is representing as 10 power 10 ohms. So this is a very high value, that means representing as open circuit here in the circuit model, and low value it is representing as short circuit in the circuit model. So NMOS is acting as a switch for both values of inputs logic 0 and logic high. Logic high on switch, logic low off switch. That is, an N-channel MOSFET or N-MOSFET is the basic element in a family of devices known as NMOS, and drain is always biased with more positive related to the source in the NMOS, and here gate to source voltage VGS is the input voltage which is used to control the resistance between source and drain, and it determines whether the device is either on condition or off condition. That is VGS. VGS determines whether the device is in the on or off and based on the resistance values, which we have seen as a circuit. Next, Pmas is also using as a switch. So Pmas is complementary to the Nmas. It is representation. The source, drain and gate will be represented here. For the VGS, this is the VGS and VTP is some negative potential. So whenever VGS is less than of VTN, the Pmas will be on, Pmas is on, or we can tell like this also, VGS, mod VGS is greater than mod, sorry it is P, mod VGS is greater than of mod VTP, this Pmas is on. And other condition, that is when VGS is greater than of VTP or mod VGS is less than of mod VTP, then for these two conditions Pmas is off. Pmas is off. Off means open circuit with high resistance, on means low resistance with short circuit. So when the voltage conditions are satisfying like this, Nmas will be on or off. That means when it is on, using as a short switch. If it is off, it is using as a closed switch, open switch. Let's see that as a circuit model. This is our Pmas transistor. This is the gate terminal and this is the source terminal, and between these two potential is VGS, and depending upon the VGS and VTN value, this transistor may be on or off. That is, for the logic high value of input VGS, the transistor is in the off condition. For logic low, transistor is in the on condition. On means low resistance, it is representing as 10 power 3 ohms, and off is high resistance. For example, it is representing as 10 power 10 ohms. So off is representing as open circuit and on is representing as here closed circuit. Closed circuit. So this is the Pmas switch. Therefore, Pmas is also acting as a switch for both values of input logic 0 and logic high. The same is written here. The P-channel MOSFET, that is a Pmas, operates in the same manner as the N-channel but with opposite polarity of voltages. That is, voltages of opposite polarity. And the drain is connected to the lower side of the potential when compared to the source in the source for the Pmas circuit. And to turn the Pmas on or off, the voltage is required. To make the Pmas on, voltage is required lower than the threshold voltage VTP, and to make it off, the voltage required more than the VTP value. That is, voltage at the gate related to the source must be negative to make the switch on of the Pmas transistor, which we have seen in the previous slide. So basically, Nmas and Pmas are acting as switches based on the input values. Input logic 0, Pmas is on. Input logic 1, Pmas is off. Input logic 1, Nmas on, and input logic 0, Nmas off. So perfect switches. These two are acting as open and short switches. Another application of the MOSFET is used as amplifier in analog applications. So this MOSFET is acting as amplifier based on its gate potential and current relation. So by applying a small voltage at the gate terminal, ID will flow, drain current will flow. That VGS and ID relation is explained through this figure. See here, x-axis is here gate source voltage VGS input voltage, and y-axis is representing of ID. For certain voltage of VGS, that is less than VTH, device is in the off condition. It is representing of Nmas. It is the Nmas transistor. So less than VTH of VGS value, the device is in the cutoff, therefore no current. But once after VGS is increased than the VTH, the current is following this relation. Now input is applying as VGS and output is taking as the ID. The gain is nothing but here GM, delta ID by delta VGS, that is also called as transconductance. See, for a small change of VGS, there is a large change of ID. That will give the amplification action for this MOSFET. Now, by having of this relation, let's apply some another signal here to make it amplification. That is, so along with this VGS, to make it switch on, input signal Vi is connected, then that Vi signal, this is the Vi signal, that Vi signal is amplified here, this is the output signal. Observe here the magnitude of input value and output value, that is the change in this VGS, this is the VGS, and change in the output current, that is equal to this much change. So output change is higher when compared to the input change, it is called as the amplification part. So like this, MOSFET can be used as amplifier and MOSFET can be used as a switch, and so therefore MOSFET can be used in digital applications and analog applications. Therefore VLSI ICs which are used for analog and digital applications can use this MOSFET. Only MOSFET can be used instead of other components also. So therefore packing density is more and reliability more and speed is more and power consumption is less for these VLSI ICs which are using the MOS transistors. Now because of having all these advantages, this MOSFET is used in so many applications. Those are applications of MOSFETs are used in digital integrated circuits, ICs, such as examples of microprocessors and microcontrollers, and these are also used in memories and CMOS logic gates, used in microprocessors and microcontrollers, used in memories and logic circuits, and it is used as switches, and these are also used as amplifiers for the amplification purpose and for the oscillators like analog applications. In both analog applications and digital applications, all the applications, this MOSFET can be used, and this is used in all the arithmetic circuits, that means this is used in calculators, computers and etc. These are the applications of MOSFET. The advantages of MOSFET are, MOSFETs provides greater efficiency while operating at lower voltages. So it can operate with lower voltages and it will give greater efficiency. And the absence of gate currents results high input impedance. The absence of gate current means because of the structure of mass at the gate, that gate is insulated with, this is oxide. Gate is insulated with oxide. Therefore, because of this insulator, that gate current is absent. Because of that gate current absence, it results in the high input impedance. Input impedance is very high. And they operate at lower power and draws no current. So, operate at the lower power and draws the no current. Therefore, it is operating with the lower power. It takes the lower power consumption and low power dissipation also. And it gives the high packing density because of using the same transistor for all the components. And the cost is less, that is, it is a low buying cost and low manufacturing cost. These are the advantages of MOSFETs. And limitations of MOSFET. Only one drawback is there for the MOS IC, that is, its operating speed is less when compared to the bipolar ICs. Actually, its speed is not less, but its speed when compared to the bipolar ICs, its speed is less. Therefore, these are not going to be used for very high speed applications. For very high speed applications, only if a speed is only the constraint, then instead of mass, bipolar is the better. And the next one, because of getting the more packing density, more number of components on the IC, the transistor sizes are reducing. That is, scaling is using for the mass transistors. So when scaling is applied, when the channel length is reduced, then the operation is going to be a problem for that because of the short channel effects and because of the second order effects and etc. So the small size of MOSFETs has created operational problems as producing such a tiny transistors. Tiny transistors is an enormous challenge. When taking a tiny transistor and getting the correct operation without affecting by the short channel and second order effects is the problem for the mass transistor. These two are the limitations of the MOSFET. The summary of this lecture is, till now we have seen MOSFET introduction, mass technology introduction, and MOSFET structure and MOSFET's types of enhancement, depletion, NMOS, PMOS, and then the structures, schematic structures and 3D structure of this MOSFET, and the applications of this MOSFET like a switch and amplifier, and we have seen the applications, advantages and limitations of the MOSFET. So advantages and limitations we have seen, applications and its switch behavior and amplifier we have seen, and the MOSFET structures and symbols for both enhancement, depletion, NMOS and PMOS transistors, with starting with the types of the transistors from BJT and FET we have seen in this lecture. I hope you understood this basics of mass transistor. In the next lecture we will see the operation of the mass transistor. Thank you.